We have all the three models here.
Yeah.
Hello, air, and
So, I don't know, who's that? Me or you?
Yeah, I'm just standing here. There's something to
Yeah, so everyone welcome.
video. Nobody knows otherwise. It's just a background noise coming from the guy.
So the closing?
I don't know.
Yeah, it is, so we could have, okay. Okay, welcome everyone to your class 2 continuing this previous talk of matrix models. Please.
Thank you. So since everybody remembers what I did last time, since everybody was paying good attention, first recap from my minute. So we'll start with what we did last time was we had a matrix model that had partition functions within one list. And for an arbitrary potential. So it's in zero space time dimension. We had partition function like this, and we wanted to calculate the correlates and everything. So in order to do that, we had to first find out what's the measure. We have to get what how to calculate for some arbitrary insertions inside. We have to get how to take care of this volume term. So what we try to do, we try to gauge fix, and out of that then we shift it to this eigenvalue notation. So then we then got this particular form for partition function given by where this is we'll take care of this later, and then we can try to regularize it. And this is the method is just now after diagonalization, the method is eigenvalues. And then the value couple term you get is something called value mode function. And the explanation is just instead of having this kind of term, we just have the same potential, but in terms of all the eigenvalues. From here, we did all that, we go here. Okay, good, we have something like this now. So how do we solve it? In order to solve it, we saw that we need first to know what the form of potential is, and we need to see what the eigenvalue distribution is like. So once we have that, we realized it's just not that directly easy to solve. So we introduced something, a new term called resolvent. And in order to properly have a resolvent at leading order and so on, we decided to change the action and try to do something like this, and call this entire term effective action. And then said if we have large n, we are basically doing a saddle point approximation. So we had to do something like that. And then we introduced the resolvent term that we try to do is given by something like this, which can be expanded in powers of m by e, and then ordered by genuses and so on. So after doing that, we saw that for this case of leading order, just by knowing the potential, the form of potential and form of eigenvalue distribution, we can get a leading order term for the resolvent. And then for the simplest case of Gaussian model, we were able to see what the solution was. So that's where we stopped last time. Okay, well, at this point, it's just a perturbation theory for some very real case. What's so special about it? That is something we'll see. In order to do that, we will start with a more generalized partition function. Yeah. Instead of this, we call it this. We will now take something like this. Instead of 2, we have some quantity called beta. and this will remain the same. We'll not worry about the normalization for now. And the exponential will this encapsulates all of the eigenvalues. So like it's just there's a common and everything, but this is just how to write it. So okay, why have I like the only difference I know from the one that I've written before is we know the normalization for now and added this beta here and here. So what is beta? Well, last time when I said we looked at general matrix model, that was slightly fibbing. We started looking at general matrix model. We were looking at something called unitary Hermitian matrix model. For that, the beta is equal to 2. If we have something like there are two other classes, the main difference is that in case of the one we saw, the eigenvalues are complex numbers, but there are other possibilities where you can have complex numbers. Mean you can have the eigenvalues be real or quaternion only. In case it's real, beta is 1, for complex is 2, and for quaternion is 4. So we can, these are the types of like different types of matrix model we can have. Then more general terms, we will see when we try to try to solve for try to get a general way to a standardized type of equation. We'll see why beta equals 2 is actually a very special value. So we have something like this now. Now, what we have to do is that, okay.
But we could generalize and repeat it be right?
But they do not correspond to a specific concept.
No, it doesn't correspond, but we could generalize.
We could, yeah. We can be anything, but
This is first principle.
yeah, I mean, but
You cannot rewrite it in terms of metrics interval.
no, you can try, but the space that you get out of it is not very well defined. You don't know like how the eigenvalues behave. You don't know what is going on in general. Beta that you get out of here is something that you get after like gauge tracing, right? So
Sure, but you can just take that as a starting point.
yeah, of course, yeah. You can take this as a starting point and then later say this corresponds to having this kind of symmetry and so on. Yeah. But so that is exactly what it means. Beta is what we have like the specific, like if I remember correctly, it's OM, and we have like real eigenvalues for beta equal to 2, it's complex and UN, and I forgot what it is for beta equals 4. Quaternion and something like that. So, but yeah, you can have it in general. So we first need to have some insertions here. So in order to do that, we will first explicitly state what kind of what is the V lambda, and the V lambda is something like some like V of n. It's the same thing that we had before. We'll have similar definition for lambda, of course, but V of n will be this is the kind of potential we did there. So it's not costing anymore. So
And I guess P is upstairs and you also have S.
yeah,
You mean G?
P the P and yes, yeah.
Okay.
Yeah. I mean,
Sure.
yeah. So we want to insert like these kind of terms here because that corresponds to having different kind of diagrams. So we will define something called a loop insertion operator. What it basically does is extract this term alone from the exponential. So that is defined by an operator.
And I guess you go on minus B because you already have minus.
This is the convention.
Huh?
Okay, I think it's plus.
That would make more sense.
Yeah, it's plus if there is a minus outside. But yeah, the ultimate thing is there should be a minus. But yeah, you're right, sorry. So yeah, if you have some like this, then you define this to be. Essentially, what it does is it extracts this divided by p mu y terms. If you act this on z, you get tracer m power p by p mu, the m power mu I by p power mu I kind of term outside. So yeah, and since it only acts on the coupling constant, you don't have to worry about whatever side. Now, if you have something like this, we now want to say, okay, let's try to do some n number of general insertions. So acting like n times here, we will get something like this. Yeah. I'm assuming that, like, I'll start with the already existing such trace term. I'll explain all the terms, all the things term by term, but small n, not large n. Yeah. So what have I done? This is the measure. This is the beta one before. I instead of starting directly from Z, I'll just say that it's just that there's already a place over here. Now, what have I done is I'll add this kind of insertion on this. So what I'll get is I'll get tracer FRP by P mu I term below. I'll extract a term like that. Now, after that, what I want to do, I want, since I've like defined resolvents to be something of this form, I want something like this to come out. So what I do is that I take sum over all of the y's. Once I take, and like since we take p to be large, n power p by p power mu y, n power mu y by p power mu y, if I sum it over, I'll get these kind of terms. Is that clear? I jumped a few steps, but
Yeah, it's geometric series, I guess.
yeah.
But why wouldn't that be without the mu I downstairs? So it looks like it's differentiated. You have a mu I downstairs.
Yeah, here.
Yeah, but upstairs, I mean, that
Yeah.
one.
Yeah. That is to ensure that like I'll have a proper geometric series.
Okay.
I want like I don't want to just like extract this kind of term, but I want to get something like this. So if I add this on this and take a sum over mu y, I want to extract the inverse kind of expansion. So I define my extractor like the loop insertion operator to be something that gives me all the geometric terms at some random values. And since these are multiplicative, all of these are multiplicative, I can just take a sum individually and like set all of them to be going something like this individually.
So where's the small n coming from?
Like I insert n number of objects.
Oh, okay.
Yeah, so I'll rehash. I'll insert n number of objects, take some over mu I so that the geometric series comes out. And I already have an insertion beforehand before I go on this. I'm not taking Z, I'm taking something like this to begin with. Already an insertion I have. Okay? Yeah. I have something like this. Now, this is not equal to anything. So, but we know that if I'm doing some path integral, if I take some, like if I have some kind of like partition function, like if I take some derivative, we know that from this space, there is no proper boundary terms or anything like that. So I can insert some kind of like derivative, this kind of derivative inside, so that I can like set this whatever term I get inside to go zero. This looks very suspicious from the point of view of eigenvalues, but what happens is you essentially are like taking a derivative with respect to the matrix components, so that whatever integral you have, they should not have any specific relation to any matrix.
I mean, you're basically doing the same as we do when we divide the swing and dice.
Yes, exactly. Yeah, these are the
We,
swing.
you have a total derivative on the integral.
Yeah.
And then you assume that the boundary terms vanish.
Yeah.
And they do it because it's exponential surprise.
Yeah, I mean, it's not just that, it's like, this is not a normal space. Right? These are, so,
Yeah.
in this space, we say there is no, like, there is no boundary term, that's by construction.
Yeah, you assume that, it morally, it's often the case for the potentials that.
Yeah. Yeah, of course. Yeah, but here you do not have to depend on such arguments. You can just say, in case of matrix model, the bounding spaces, you don't have to, like, those have to go to zero. That's the space is by construction like that. Yeah, so now we have something like this. Now, then we try to insert our derivatives, so it's now just. Instead of this, I'll make couple substitutions so that my life is easier. I'll just write d lambda, so this becomes this. I'll have this term will be the same. These kind of multiplications, oh, sorry, this shouldn't be multiplicated. I'm sorry, this should be the case. Since it's, it's like this. Yeah, instead of this, I'll just write. This is not in resolvent, but we are running out of variables. We have that okay? Oh, sorry, I forgot why I did this. Yeah. This derivative, like the derivative I'm introducing, and I'm substituting all these terms to, so that they're smaller. Yeah. So what do we do after this is that we try to expand and try to solve for this. The calculation is a bit tedious, but the end result I'll try to explain. So what we're doing is we want to okay, so since the substitution you can kind of see where I'm going, then actually when I have to have like this inside a proper integral, these things are code, like these are resolvents which have a geometric interpretation inside proper integral. So what we want to do is that okay, we have something like this. Now what do you like? If you have something geometric, then you have like you have physical constraints for it. So the physical constraint that we will expect out of the equations that we follow is that one, they have to represent something called a connected diagram. What are connected diagrams? They have to be connected to this. Like this is the initial point from which we start to calculate. These are the insertions that we have done. So the diagrams that we get, like the loop equation will be clearly will be called connected. So yeah. Another thing is, like the main thing that we do before is like try to differentiate with the boundary term and set the boundary term to zero. Here we don't want to like extract boundary terms. We say use the fact that the boundary term goes to zero, and then take the derivatives inside and like act as derivative upon everything and continue with the integral. So that when this integral acts on this, we know what it is. That is the resolvent. That's our like, initial definition. So yeah, we're back to something that's more relevant to what we want. And this, since we have taken beta, the resolvent is not the same as just integrating this. The resolvent in case of general beta is given by some Wn. Yeah. Okay, what have I written?
Do you want it connected?
Yeah, connected. So what have I written? Just n is if I have if there are n terms here. So I'll instead of writing this every time, I'll reduce it further to something like this.
But only you also already had a
Yeah,
bracket
it's
on
a
that.
different, it's a different.
omega.
Yeah. This is what like this one is this without the integral. The same thing, but without the integral. But after integrating,
Okay.
like I.
And maybe you should then write a little c to remind that this is connected.
Yeah, this is something. Yeah. Yeah, this is the connected diagram. And for connected diagram, after making substitution and solving for all of this, we get. This is the long expression, so bear with me.
Capital I is some indices, index set. And capital I is some index set or argument set.
Right.
Capital I is some.
Yeah, capital I is just like, all of these.
Yeah.
This is like, it's a set of all points that have inserted.
Yes.
Yeah. Okay.
Yeah.
In case beta and beta are confusing, let me know. Problem. Not use the same. Yeah. This is equal to. Yeah. This is the loop equation. This is called the loop equation for connected diagrams. So what is this? We have two insertions at P, and this is connected to all the extra insertions that we had at series of n insertions that we have had. This is like if you have a diagram that's where like you have one that's connected here and one that's connected like something like this. This is like, you know, I minus the set of B is kind of like connected to a point, but they're not connected to the set of B. Points are excluded geometrically, and I do not know what this means geometrically. Like, what is the derivative of a diagram? So then you have like things like this, where you have one that's exclusively not connected to a specific point, but then you like that without getting connected, like, you know, you have one insertion, but then that specific point is not connected to anything else, kind of diagram. And this is, well, these are the terms that you get from the potential. I do not, like, they do not have a very specific geometry determination. So yeah, this is what you get for connected diagrams.
So how did you arrive at this from your previous, like, what's the type of calculation? You did to.
Yeah, yeah, so,
It's just when you're writing.
Oh,
yeah. So, yeah, so these terms,
So this omega, I mean, I can understand if you only have one insertion, then I guess it would be sum over 1 over p minus lambda. But omega is a small insertion. How do we generalize? Is it an arbitrary function of all of them, or is it's this 1 over p minus p1 minus lambda sum over?
yeah, it's like this.
And P, this would be P1 and P2 and P3 and so on.
Yeah,
Right, okay. So it's a very specific,
it's a very specific, yeah.
so it's product of resolvents.
Yes, yeah. I mean, well, like, yeah, when you say product of resolvents, like, there's implied like, kind of connection there, meaning like, the fact that they're connected, but as we see, it's not necessarily the case. These are not resolvents, they are still inside the integral.
Sure,
These are resolvents.
sure, yeah. Yeah, I'm misusing this, but it's
Yeah,
technically.
yeah. So, yeah, this is why this term is exactly why beta is very special, because this derivative is, well, it's not exactly easy to compute, nor is it very, like, you know, well, like, what does the geometry mean? Is a big question. So this specific term vanishes for beta equals 2, and this kind of normalization also vanish. So instead of just writing, you know, just kind of omega, we can just take the omega out, and that will just, like, you know, we can redefine omega to be including the like, you know, the kind of correlator, and then that's, like, you know, these kind of terms vanish, and it simplifies it very much. That is one reason why beta is special. And this is one reason why matrix model is special. I mean, of course, when I write something like this, it's like, you know, what are you writing? So, for if I just like remove, you know, if I just have one single insertion, or even like, yeah, if I have one single insertion, you can kind of see that, like, before these are the kind of flows that we want. For example, like you can calculate like with just your normal matrix model without doing anything special. You can calculate for n is equal to 0 what the specific like without using this equation, you can calculate for 0 insertion. That will be like omega 2, the W2 here, and when you have W2 or W1, what it essentially says is that like, if you want W3, it's just like you go through the motions of calculating some combinations of W1 and W0, and that's it. Like that is pretty much enough to ensure what you want, like your high order kind of coordinators. But this, like, there's one huge caveat here, is that I haven't spoken about the genus expansion. Well, you can do like this equation can also be derived for if you want to like have ordering based on genus and the number of insertion. what you do is that last time we defined this like resolvent to have this 1 by n power kind of ordering. So we just insert like for n plus 2, we just insert like 1 by 2 of n power 2g plus n minus 2, or the other way around. Anyway, so we insert that kind of expansion for omega and take the sum over them, and then collect all the terms that are at the exact power of n. And that will give you a more, even more general like equation for an n insertion G number of genius loop equation for matrix model. But like I said, so even if I insert that, then you can see that even if you want to calculate like the main point is that if I insert n here, you can see like if I want to calculate something, if I have a couple of genus zero terms, and I can calculate without using anything like this. If I can calculate genus one term, which is a bit more complicated, but it's not too difficult to do, I can use without touching the matrix model, like coordinate this, I can just use this and get everything else. So in general, you need terms like omega g comma n is what you need. You have to calculate 0, 1, 0, 2, and 1, 1. If you know these three, you can calculate this.
Can you remind us what is the genus in the message model? I mean, where does the genus insert?
Remember we had diagrams like that is where the genus comes in. Yeah, so that's the like, crowning achievement of having something like matrix model. So yeah, now our work with matrix model is done. I'll move on to taking that. So yeah, gating gravity. So what is gating gravity? It's defined as an action to imply this. Or the regular terms that we usually encounter in gating gravity. And then we said the curvature will be -2. And this is the general that theory. This term says R -2, and then there should be a corresponding boundary term.
So the second term is like a one-dimensional multiplier of
Yeah.
condition.
Okay.
And the first, yeah, okay.
Yeah. So yeah, this is the entropy, and yeah, this is the Lagrange multiplier, and this is to keep everything straight.
So I'm assuming n is three-dimensional manifold? Or?
Yeah.
Okay.
Yeah. So this is just with topological terms. This is process high.
What is A?
Huh? Exterior, I mean, the extrinsic curvature, the
Contracted.
boundary.
Contracted with dimension.
Yeah. Yeah, so okay, we have this action. So now
And does phi have a name?
division.
Divisor?
Yeah.
And is phi the same on the main one and the boundary of the main one?
Yeah.
You can do that.
Yeah.
Okay, so. Okay, because they live in different places, then yeah, effectively it's two different phis.
Yeah, I mean, it is different in the sense that like if you want to define boundary versus a different thing, you also have to specify a separate different kind of condition for what like, the behavior of the network. It's not like directly obvious by this setting, from the, if I just set metric to something, like it also sets, if I set metric to, like, say, have some specific, with this limit in our inner coordinate is the boundary, then that automatically takes it, what the delivery has to do as.
But I guess when we talk about Lagrange multiplier, then the value of it is not so important. I guess we could call them two different files. I mean, is it something one by calling them the same name?
Yeah, I mean, the thing is, these files are same as that when you try to like
Take the
get a
name.
boundary term, like this is the like value correct is given software. So if I try to get like what the proper boundary term is, it's not that I can just choose a general file. It has to be the same.
Oh, okay, they are related by that
Yeah.
variation. And X0 is just a constant?
Yeah, it's the entry. I mean, it's.
Why do you want to set R2 minus 2?
Well, we need to have a constant negative curvature radius.
For radius.
Yeah, I mean, this is not exactly ADS, this is something called real ADS. ADS is like, normally have, you have a proper space with dimension and everything here. You say, all of that plus there's a boundary cutoff. That makes it nearly ADS. And that boundary is kind of some like large inner radius, so
No, there's nearly ADS2.
yeah, nearly ADS too.
Why do we need radius 2?
I mean, by construction, it's nearly ADS too.
Yes, but what was the reason of just writing that action?
Well, you can define JT gravity more generally, right? You don't have to put two there, you could put any content. You could do it in the sitter, for example, you could.
Yeah. But
But I think you want to talk about a duality.
Yeah,
Matrix
yeah.
model, so that's what you want ADS.
yeah, I mean, the duality does exist for it was like 3 weeks ago or something, and they came up with the duality for de-sitter as well. But in that case, well, the matrix model is not very well. I mean, physically, it has. I mean, like as you know, we did large n ordering and everything to get the matrix, but for if you do it for de-sitter, you have to take large minus n.
And you can probably scale the ADS radius to 1, I mean, in so low dimension.
I mean, it's
So essentially it's 2 and not capital lambda.
yeah.
Anyway,
Yeah, I'm not sure about that.
Just a choice of dimensions.
Huh?
Just a choice of dimensions.
Yeah. Okay, so yeah. Yeah, so anyway, we want to look at connected diagrams. So what are connected diagrams we have here? We have like certain number of boundary terms connected to an inner space. So what kind of space, what kind of boundary do we have? So we want, let's say we have something with n boundaries, so we have something like the product is you want something like this to n, and then this is the item that like this is the quantity that we want to calculate. That's our goal here. And
I runs from 1 to little n.
yeah. And we will also like define like the quantity where it's just an integral transform of integral partition function. Yeah, this is another thing that we will have. For now, we know what
So shouldn't the IFE on set or we see so beta is inverse temperature?
beta is the boundary data, circumference of the boundary that we have. So yeah, what geometrically what it is like you have these kind of something that's connected to like something in the bulk here, and beta is the circumference of this yeah, the boundary. So yeah, we have like for example, if I want to do like two boundaries and then like genus two, I'll have yeah, this is the kind of this is genus two with two boundaries. Here, of course, we haven't like taken genus ordering into effect yet, but yeah, if you talk genus, it's with something in the bulk with two counter boundaries inside. And they have radius beta one and beta two. Yeah, so now we have something like this. We will define the genus ordering as something like this. Z is no longer a partition function, it's just some function which satisfies this equality that run. Yeah. So as you can see, if I have something here that comes from the action, this particular full term will contribute to the ordering. And ZGN is essentially integrated integral of the path integral contribution for these two.
Is chi the Euler factor?
Yeah.
So T is the genus?
Yeah. I mean, yeah. Yeah. So now, what is ZGN? We need a proper definition of that. That is an integral over the bulk multiplied and then over boundaries. So here there is another difference. In normal classical JT, the diagram I just drew, it has a perfectly circular, perfectly circular boundaries. Yeah. But we don't want to just do normal JT gravity. We try to have some kind of, we try to take it to have classical solution plus some quantum corrections. Those quantum corrections are geometrically of something called boundary wiggles. So essentially, instead of having something like this, you have something like that. The white part is what we have classically, and the orange is the corrections that we introduced. So this is the boundary wiggles, and then
But the trumpet itself is not a classical solution, I think.
no, yeah, it is. Trumpet with proper circular boundary is a classical solution.
I mean, it does have the R equals -2 constraint, but I think it breaks on symmetries that
Yeah,
such that it is not like classical. That's why you put the wiggle boundary there. But
no, trumpet is classical. It does break the symmetry because normal disks have SL2R symmetry.
yeah.
Boundary, the trumpets have U1 symmetry, but it is still completely classical. I mean, like, well, by classical, I mean, you can, without any wiggles, you can just like write the boundary action, like, and then from like what we get here, and then try to get a solution for the equation of motion. That will just give you perfectly yeah, perfect classical solution that has no, that just has perfect circular boundaries connected to something inside with a geodesic in one end and boundary at the other. I'll come back to that. I'll come back to boundary.
Yeah, we are just maybe misusing the terms, but it's, I don't know, I was, I had in mind that the trumpet itself is of course an hyperbolic space by definition.
Yeah,
But the point is that whenever you have the boundary fixed, that's fine. But now you're moving, that's what you call near the ADS2, and the boundary is dynamical. And that does not come directly from the equations of motion, I think.
yeah. When you have like, yeah, that is not classical. Yeah, the one you get after all this is not classical. That's what we want to calculate.
Okay, yeah, then I misunderstood.
I mean, like, without doing any, like, without introducing any wiggles, without like doing anything, the normal JD gravity has like one that has a perfectly circular boundary, and the other end has geodesic attached to it. That is classical. This is not. Yeah. Yeah, we have these kind of like. I mean, another important thing is that this separates into one over bulk and the other over boundary. Now we have a problem, is that the bulk here is given by something called like a Weil-Petersen moduli space. But it's very well defined, it has its own like volume form and everything, but that's a catch. It has it has a constant that you have to fix that amounts to choice of units. But you can't just fix it, you can't just use the choice of units that you want and then expect the boundary to be perfectly defined. Because whatever you choose here will obviously affect what's going on here. But since the integral separates out and we currently, like, if you just proceed the integral as usual, we'll have an extra constant that you have no way of fixing without knowing what its effect is on bulk. So what I mean by that is that if I have, say, I'll just do some genus 2. This is genus 2 boundaries that we have done before. So if I want to have here, that's okay. Anyway, so yeah. The point is you can try to decompose the space into these things called pans. What are pans is that there are 3 spheres. Now it's very good. So your entire bulk can be constructed with all these pans. But the problem is like that has a like the very Peterson form is given by something like this. So what have I written here is that this is the geodesic boundaries for each sphere. This is something called a twist parameter. So whenever you try to glue 2 pans together, you need to know the boundary has to be fixed, and so that you have to twist them so that they join cohesively. So each kind of like inner space has this form where K is the number of you have like K number of in the space has 2K coordinates where K is determined by the genus and the number of boundaries that you have. And this is a true form, so you have a 2K number of coordinates inside. But this is if you have like a parasitic or possible Weil-Petersen form, you like the Weil-Petersen space, border space, this is the Weil-Petersen form you have. This is also like that space is also like a space with a Taylor manifold, and you can get the volume form by like having a number of edge products. All of them good. but now you have this. How do you, like, like setting alpha is equivalent to like having a coordinate choice. So you have a problem. What do? You can't just take an arbitrary value of alpha and then expect everything like calculate your probably separately and say it's fine. So we need to connect those two. To do that, what we do is that we try to write we try to write it in first order formalism. These terms. Yeah, we try to do that. So it's like, since it is 2D, you don't have to worry too much about the spin connection. And you can go like, before we do that, like, yeah, you don't have to worry about spin connection. And you can just write R as yeah, this is the definition in 2 dimension. So yeah, this will give you this is just what you get here, and then yeah, this is what you get. Now we can try to write this in and yeah, so we'll try to include this.
I guess the EA are 5 lines.
Yeah. We have to like, try to first order formulas in EA is EA is given by this, then for a spin connection, we have some omega. So once you have it, they are raised going by this delta AD. No, so yeah, now what RAD like has similar construction.
So, let's see, what's written omega AB equals.
Epsilon AD, there is a beta. Yeah, so there's yeah, so the full definitions, and we try to substitute the terms we get back to R plus 2. And we have to remember that since we have transformed to this, there is this load torsion conditions that we have been imposed by hand. This is that yeah, we have to impose this by hand along with the normal thing or normal definitions that we have written. So if we do that, this becomes we introduce new Lagrange multiplier to enforce the load torsion partition. Yeah, this is what we get. And this we can write it as something like this in what's called background peak theory. So what is B and F? B is just the matrix of scalars that we have built on the Lagrange multiplier.
So what did you say, how is this called?
Background peak theory. Now, why do we do that? Is that like background field theory has a well-defined boundary condition. So if we write this and we take boundary condition, then we can see we will try to like our motivation here is that we have this kind of formalism we'll try to get the symplectic form that we have defined for well-fitted space from here. Because what we have done is rewritten into something like this. Here, the volume form and the proper symplectic form for the molecule are here. You can you have a well-defined boundary condition here. You can also get a symplectic form for the boundary here. But here, and which are actually interrelated. Here we have the problem of not being able to fix the constant in front of the biological form without affecting the boundary, or rather, we don't know how to change the coordinate constants in the boundary so that we will have proper terms like correct and bulk and like the correct choice of coordinates. So yeah, that's our motivation. So we try, and we know that here we get the bulk is very Peterson form. So what we want to do is from here try to derive try to get the very Peterson form bulk. Right, so that JT, which has power, is this y%, and the boundary, which is you will see soon what the boundary becomes, and then we have something very in this equivalent to BF, which has a bulk and boundary, and and these are also connected by a well-defined boundary condition. We do not know what this is. So we go here, we try to get the bulk, we try to get the very Peterson form from here. We get this from here, we go to the boundary, and here we set the boundary condition. That is our motivation. That is what we need to do anyway.
I don't erase.
Okay, sorry.
Take the other.
Yeah, I'll take it. What time do we have? I'm not sure. Yeah. What's time now? 3:30. Yeah, try to wrap up soon. You're near the end anyway. Yeah, so where we stopped, we wrote something like BF, what is B, what is F? Didn't say anything. B is, I don't know why we had a ion when it says convention, but we have one side usage. And F is a definition version of pairs.
So how many files do you have? You have file 1, file 2?
Phi 1 and phi 2 come from this. The node torsion conditions that we said,
Yeah, yeah.
and phi is the original electron. Yeah. We have this. So yeah, now that we have this, for flat conventions, that is n equals to 0, people have found out that the symplectic form is given by something like this. What are these? These are the these are deformations to the gauge field here. If we have two arbitrary deformations introduced, then that will induce a measure that is given that will induce a measure from with a symplectic form given in this format. This is not the same alpha as before. We're just using a constant here so that you know how to compare. So now that we have the symplectic,
So alpha is just a constant.
It's just constant.
Exponential constant.
yeah, it's not the same as before. So one for variables form.
Okay.
That's different. This is different. This is alpha.
But they are constants.
Yeah,
not like sigma and n.
No.
Because they're variables.
No, these are constants that are equivalent to say,
Yeah, then more like.
Yeah.
Yeah. So they can vary, but the alpha is some
Yeah.
constant.
Yeah, some constant, yeah, you're right. Yeah, so now that we have here, what we want to do is that we want to introduce deformations. So we have to calculate this. We want to introduce deformations that are linear up to second order. So what does it mean? Is that if I use some up to order epsilon squared, whatever deformation I introduce, if I have a equals to some a, I should still have the a equals
Shouldn't it then also be delta? P delta?
epsilon.
So you're making a variation of the flatness condition, I guess.
Yeah,
So shouldn't it be the first A be dA delta A, D delta A?
sorry, yeah, you're right. It should be like this, yes. So yeah, this is the condition that we impose for some deformation to capital theta. So now that we have that, we will focus on a particular metric that is given like this. What I written, T is the trace and B is the genus and continent that we know from before. Well, X is a it's a discontinuous coordinate that we introduce so that you do not have multiple twists trying to identify with the same choice that we made. Like, of course, since twist is cyclical, you have to introduce something like dx to ensure that it's a discontinuous coordinate that resets back after you move a certain amount, so that you do not have to worry about multiple twists being attributed to the same kind of the same coordinate. Then you will have a load counting that you have not accounted for. Yeah. So this is the matrix. So with that, this is like E1, you get E2 from there, and then with E1 and E2, you can get omega. And then if you introduce two such deformations, so here, two such deformations that are compliant with this condition, you get And that's, yeah, which is again, going back to the private interest in form. We've just expanded the bench product and have uh, information driven out. So now we have retrieved what we wanted there. We have gone from BF to JP. We also gone from like related the bulk here to when pages in there. Now we have to go from bulk here to boundary. In order to do that, we need to have boundary conditions. So we come back, we are back here. So the boundary conditions for JP guarantee is given by these set of these sets of conditions. So U is the U is a parameter of like U is the coordinate of the boundary. Like whatever the curve we have there is parameterized U. So this is the boundary conditions for JP gravity.
And gamma.
Gamma is constant.
Epsilon is new or the same as for the definition?
No, it's something else. It's just anything small is epsilon. So yeah, so
It looks like the regularization parameter that you use in AES 15.
yeah, but here you don't try to use that to, this is just to, you don't use this to go to something else. This is it, there's a boundary cut off and that's all. You don't, try to.
Yeah, that's also what you do in the AES 15, like for regularizing or.
Oh, yes, you're right, because you do the same procedure and you retrieve a CIP. So, yeah, that's, we essentially want to see the action in the boundary, whereas in this, ADS, the cat's out of the bag, it will be a CIP. Yeah, you're right. Okay, so with this, you can try to get this roughly translates to having large row here. So yeah, with that, we can try to get the variance for the boundaries, which is given by so here. This is yeah, when you try to take large row, and then from this metric, like not from this metric, the general ADS metric with d rho plus cos h square of rho square plus the t square, d tau square, you get d tau square, yeah, you get when you do large row expansion, you get something like this. Where SAH is the Schwarzian, is it's actually Schwarzian of some function t, where this is the tau from normal hyperbolic ADS, like normal like tau from the metric you get for ADS two. This is like a short version of writing that is this Schwarzian u. This is what it actually means. And yeah, like I said, you parameterize this the boundary. Is that okay? So now that we have this, we also have this part, the bulk for BF going to boundary and the condition to boundary. So that from BF really is given by this is the condition for the boundary condition, where C is a constant, I, and then like a U because we have written U here. And we have to remember the fact that if we want to calculate this again, you have to keep in mind we have new things. And this is again applicable. If you do that and try to calculate, you can get the boundary action.
And AU means differentiation in respect to U, or?
Yeah, the U because that's the boundary coordinate that we have. It's just to denote, it's just to denote like this is now my boundary. The value for which is boundary. So the action that we get is this is the action that we get.
Boundary reaction.
Yeah, if we said C to be twice gamma, that is the traditional boundary current like that, then it will become minus gamma instead of this. This is the boundary action for GT gravity. That like you can retrieve from the last part through H5K minus 1. This is the boundary action that we did derive. Okay, so now that we have that, we still do not have like we have the action, but we still need a measure to calculate the financial function, and like we need to have a we still haven't found a relation for this alpha yet. In order to do that, we go back to this. We say you still have to have a theta that satisfies this condition, but also an addition with this kind of like variance given. So if you implement that, you get a specific theta that actually satisfies all this. And that if you insert that theta, you get the boundary symplectic form to be something like this. What I mentioned before. So yeah, before we like try to deform A, it's not simply try to have a deformation that's just trying to. We already have something like this. We can just try to induce changes in the boundary, the geodesic boundary and the trace. That was the one we had before, but now we do not have either. So what's the parameter that we change in order to introduce a deformation, which is of course U. So we have something like a deformation of this form. So now that we have that, we want to see, okay, good enough. What are the conditions for external view? Of course, it can't be just simple that. So we have this condition from before, and we have one other condition, the new condition that comes up is that whatever transformation it has to preserve the Schwarzschild. So you cannot have like the boundary action completely varying wildly. So that adds an additional pressure. So like basically what happens is this should transform in this format. This is just like tau u comma u. It is like taking derivative of the whole Schwarzschild. Yeah, this is a transformation that has to be preserved for the deformation that we introduce. So once we do something like that,
Isn't this always, I mean, the definition of the Schwarzschild, it looks very much like.
yeah, it is. But
So how is that a condition? Isn't this just a property of the Schwarzschild?
I mean, like you are so the thing is, you here not like this is not just some like you do not like this is not some how do I put this
Then it's supposed to be an equation, Schwarz before u is equal to the red density.
yeah. I mean,
So that's good notation.
yeah, I mean, so like, if I have, say, like, if I have this, like, A, then like, if I have this kind of equation here, uh, like, I do not necessarily have to have, like, there will be, this is a transformation that we know. Okay, so, but we want to introduce these kind of, like, one second. Yeah. Yeah, essentially you will have, so something like d theta plus, yeah. These kind of terms start here. Theta is very general, and like you can choose whatever, like whatever the matrix elements of theta should be such that whatever you make A with, this will have this transformation built in.
Okay, so theta is related to what you call delta over there?
Here, this one.
Yeah, and that one, how do you relate, that's related to delta A?
Yeah, I mean, like theta will have,
Is that the commutator of A? Is delta A the commutator of A with theta?
yeah.
Or the covariant derivative?
I mean, like.
Or I guess it's a gauge transformation.
Yeah, it's a gauge transformation even part of this. So. This is. I mean, like.
I guess it's more or less what you wrote over there.
Yeah, so if I have like the gauge transformation should be this plus. So,
Yes, I guess you don't want to plus, okay, so. Are you saying, I thought it's just delta A that is this gauge transformation, or you say that delta A is delta transform into delta A plus this?
yeah, I mean, like, I mean, like delta A is the like, you have,
Oh, okay, it's like a one form in this space.
yes, it is.
Yeah, yeah, so you say that the one form can change with the gauge transformation.
Yes, so I mean, like, so yeah, that is the thing. This is like this one form can change. The gauge transformation should be such that like this kind of like change should like whatever the matrix elements of theta that I have here should if I have if delta A is the transformation is induced by something like this, theta should be such that this term should give you this kind of expansion. So that you're like whatever, like if A has Schwarzian in it, like if after a transformation, the Schwarzian, the elements of theta should be such that whatever the elements that you get here should incorporate all of these terms. Because like we can have like so theta can be anything here, like it can be some. Theta is something like this. So the conditions are one, it should be SL bar. The other should be that it should yeah, like this transformation, this gain transformation A going to A plus this gauge transformation should be in such a way that these elements should be such that if you have deformation, that induced deformation should also like preserve the gauge transformation, which means that whatever theta you have should take into account that these kinds of terms should appear whenever you perturb it by some external views.
So this deformation is the same as the gauge transformation or anything both? You're doing both deformation and gauge transformation? Or is
No, I mean, like the deformation is what you need to like try to get a symplectic form. The gauge transformation is a condition that has to be preserved so that like like, your theory has like specific gauge transformation already built in. You have to ensure that those kind of transformations are compatible with what we're doing here.
Okay.
So can I say that it's that this transformation should simply be a gauge transformation?
Yeah, you can like that deformation can also be a gauge transformation. That is exactly what we used to get in both the cases.
Yeah, that's what I was asking.
Yeah. I mean, like in general, that need not be true, but it's easier if we just use gauge transformation because we know how they are supposed to behave.
So for the visual minded, can you maybe draw some picture where you have this what's it called geodesic hang the tree and Swiss tower?
Okay.
Make some cartoon.
Yeah, sure. Yeah, so that's one of the advantages of JT values. I don't know that it's similar.
Yes.
Yeah, I'll just read here. So like you have these are pans. So if you want to connect it to like another pan here, these when you try to join these to geodesic, the twist parameter ensures that they gel well together. You can't just directly smoosh them. You have to twist and then that twist parameter is what you get like here, and then like this entire boundary length is V1, V2, and so on. And like yeah, so like that's how you if you when you want to figure out how many coordinates that you have for this space, this is how you determine. You initially start out with some specific genus one object, and you like manually count how many boundaries that you have, and how many like twists and like boundary geodesics that you have, and then you try to add a handle, means that's increasing genus, and then you add a puncture, that's increasing pose, and then you try to calculate, what kind of thing you have, and then by deduction, you know how many coordinates that you have. So like these are like that's how we obtain like how many boundaries, how many twists, and how they appear, and so on. Yeah. So I guess 10 more minutes out of trying that. 10 minutes. So yeah, now that we have this, they will try to get a symplectic form so that this gauge transformation will also preserve the Schwarzian transformation and has everything there included in it. So the symplectic form that we get in the boundary is given by the boundary length. Yeah, this is the symplectic form that you get. Now we can just set alpha to 1, and we don't have to worry about the effects in boundary. But for now, we will refrain from setting alpha to 1 because we do not know what was the coordinate choice that we're actually making. What are we setting? So yeah, Now we have everything to calculate what we want to calculate, so.
Does the prime, differentiate in respect to u?
Yeah, with respect to you, epsilon's functional. This is the first thing that we try to calculate. So you have a disk that has essentially symmetry. So partition function for that is given by. This is our measure of mu. Like we haven't decided, we don't know what it is yet. This is the partition function for the disk. We have a measure, we have asymptotic measure that we still haven't taken out. Then there's the Schwarzenegger inside, like these are the functions of u. So now we have to calculate it. So for the classical case, solving the equations of motion, the Schwarzenegger action is given like gives this as a solution. This is the classical solution for the Schwarzenegger action. So now, what we want to do is we want to introduce that wiggle so that you have corrections. So now this becomes.
I want to explain where the SL2 are, SUM2 sits.
Like it's because I recall correctly, it's because of the disk in the boundaries and the Swartz action has built-in to if I recall correctly.
Right.
I'm not, I don't remember exactly where this is.
I guess it's like you also have an open string at the boundary, you have some kind of.
Yeah, I mean, at the boundary, you will have the SL2R, but I'm currently blanking out on why, how to show the SL2R.
So is it like usually in string theory, it's like it's 3 points that you can put in 0, 1, and infinite.
Yeah, but I don't know why it's the case here. I don't remember exactly. I'll let you know once I go back and figure it out. So yeah, once you have this, so now we want to remove this part. So what we essentially do is that we take these perturbations such that we do not include the zero modes of SL1, which are essentially these correspond to. Of course, one thing that I mentioned here, we are only taking up to the second order derivative. So, yeah. We have to take epsilon such that epsilon equals 1 and these correspond to 0 modes of SL1. So these kind of information. So what we now do is that we expand this, we put this back here, we expand this and take only up to quadratic order in epsilon. The derivative should be up to quadratic order epsilon.
So it's like a choice.
Yeah.
I don't understand the comma. It's not a vector, it's a choice.
No. These are like 0 modes. Oh. Yeah, so, what we do is like, now, like, taking up the quadratic action, putting this back here, we get, S to be.
So I guess everyone lives on the circle. Yeah, and then these are the lowest modes actually.
Yeah.
So there's a constant mode, and then there's, I guess it's n equals 1 plus minus 1.
Yes. Yeah. Yeah, this is the quadratic quadrant, this is the thing you get, this is the action you get. So now what you do is that, keep cover calculation, you introduce, every modes for the S nodes that do more expansion, like so. We exclude the zero modes, we just write the non-zero modes. So here in the imaginary part. We introduce
You probably put an I somewhere.
here.
Yeah, but you, I guess you also go with the real imaginary, is there an I in front of imaginary?
Oh, yes. Okay. Of course, yeah, of course, imaginary, yeah. So with this mode inserts in these modes inserted, we know what the measure is. The measure is just the real and imaginary parts of the imaginary modes of epsilon. So we can insert that and integrate Z. And for this, we will get.
Should it be in equal or equal to 2?
Yeah. Of course. This is the solution that we do. So what we do is we insert these modes, and then like this integral is this d epsilon r and then I, and then here you see that like it's just a Gaussian integral now. So you just do Gaussian integral, and since like you have a lot of infinities here, so what you do is like something called zeta function regularization, and after doing that, you get this finite result for a disk. So for this is what you get. So for now we are saying this is not exactly something, dynamic, not dynamic, it's not something great, it's just a trivial boundary, it's already connected to the bulk. So for doing actually the bulk, we need trumpets. So for trumpets, we have something similar here. Instead of F into R, now it will be U1, but the rest remains the same. Yeah. Yeah, this is the partition function for trumpet, and we do the same procedure, but you get a slightly different, the classical solution of this. B is geodesic in end, the other end of trumpet. One. This is B, this is beta. So this is the classical solution. We take further about this, but the only difference is for U1, the only zero mode is epsilon equal to 1. So we complete the mode expansion, and so for trumpet, we have with the partition of the trumpet again. Now, so we have the trumpet, we have the disk. We know that for gravity, the boundary separates. For the bulk, we know if the weight is a form, and for the boundary, it's just for any number of boundary terms, it's just any insertions of this part in any trumpets. So we have this, we have this, we have this. Now we have to calculate what's in for J gravity. So if we put all of this in, this volume means sorry, this is the measure, and this is called the volume term of weight Peterson space. And then we have trumpets. Yeah, so this is what we want to solve now. We know how to solve this. And so how do we tackle this? Now, this is where we try to go back to try to find out whether this can be transformed to something that we already know from before. So before I do anything else, here you can see that these kind of end insertions will give like a specific like alpha power, minus n here. And then from here, you will get alpha power k, sorry. Yeah, since like you have k coordinates for the internal space, so k is a function of g and n. So what this shift in alpha essentially corresponds to is you have alpha power 3g plus n3 from this, and alpha power n from all the boundary terms. So I just it just gives you this. Yeah, so what does it mean? It just means that the S naught that you have for change gravity, you can just shift it by some 3/2 log alpha, and then that's just essentially because the net you can just redefine S naught, and then you don't have to worry about alpha anymore. So from now on, if you want to calculate, you can just set alpha to 1. Yeah, so we have this. Now we need to try to calculate for general Gn, how to calculate it. So in order to do that, we know what it is for 0, 1. 0, 1 is this. And we can try to do it for 0, 2, which is essentially two trumpets attached to each other. And then like what we get is basically we don't have this. And this is just like, yeah, if we get something like this and like this, we can, well, it's not B1 and B2, it's just B, since their trumpets are connected to each other to be the same B. So yeah, maybe this is like something you can do. Now, we want to, we want to see what kind of matrix model, if any, will encompass what we have done here. In order to do that, we need, what's the main thing that we need to solve matrix model? One is potential, the other is density of states. So to get density of states, what we do is that we know that like given density of like the lowest order density of state, So what I have done here essentially is that, remember we had something called like R of E that we have defined before, and it's just an integral transform of Z. We have tried to do like a reverse transform so that we, like, if you have a, like, the lowest order, what you get is the density, of course. So if you want to translate this to Z, you need to find some low mod that satisfies this condition. So what we can do, like, we already know what 0, 1 is for our calculation there. So the current unsaturated rho naught is now we can set gamma to 1. It's another choice, but we can just take that for now. So we can set gamma to 1, and this looks like, our density function for a matrix model, the lowest order density function. But yeah, so we have this. So we want to reproduce this. So how do we do that? Now we have to go for a matrix model. We'll go back to matrix model quickly and try to find out under what limits we can reproduce this. Here we go. There's our count. So yeah, it first start with the matrix model that has something like an unusual density function that's given by this. This goes between the symmetric boundary condition, single cut symmetric boundary condition. Now, what we do is that we try to remember that is ZGN. So in the original connected coordinators, there was a denominator with SE power chi naught. So we need to have that E power S naught here, S naught chi for connected coordinators of Z. So we have something like this. So what we do is that we take two scalings. One is that, like, first we shift P to going from here, some P prime that goes from 0 to 2A, then we take large A limit first. And then what we do is that we also try to ensure that, like, S naught scales such that S naught and N scale together, in which case we can replace N scaling with respect to S naught scaling. So that they remain, like, you have N, like, you take a ratio of S E or S naught by N to be some constant, and then you say I'll replace N scaling and the N ordering that we had in normal matrix model to E power S naught. So this limit and this limit is, this is why it's called double scaling matrix models. You have two specific scalings involved here. So after doing that, you get this. And this is exactly what we want there. So yeah, that is the matrix model. So now that we have gotten that, but okay, you can say we have done it for the lower order. What about higher order? That is another thing. So Mirza Kandi showed that volume for weight reducing form has its own set of recursive relation, and matrix model has its own loop equation. So I not showed that the root equation for matrix model is just like after integral transform is the same as the volume, the recursive relation for volume. But the advantage here is that like the volume is quite hard to calculate, but the root equation, even though it looks big for lower order, it's pretty easy to calculate. Most of the terms that you see are pretty trivial. So we can do that, and then at the end of the day, the resultant we get from something like this, the end is right. This is omega gn, but instead of omega we use r, and
Also, will you continue with the third part also? Will you continue with the third part?
no, that's it. This equation is over. If we take for general gamma instead of setting gamma to 1, you will also have corresponding changes here. You have n multiplicators. I protocol are here. Yeah, this is the transformation that you have. So this is the resolvent that you want, and then this is the partition function you want, this is the resolvent you can have. So that's it.
It should be DI, is it DN?
Oh, sorry, this should be I. Yeah, so. You have bound series equations. Yeah, sorry for taking too much time. Did not expect writing on this slow.
Okay, thank you. What's the speaker? If you have any questions. For the final match between the two densities, you also need to match the. I guess you are taking gamma equal to 1. Okay.
Yeah, if you like, the point that you made, like, see, at the end of the day, you don't want density, you don't want potential of the matrix model. You don't want anything from matrix model apart from the solve, you want to already have clarity. For that, the resolvent is enough. So once you do, leading order, like, you solve for leading order row, and then get the leading order resolvent, and then establish this map. You don't care about how high order frequencies behave or high order, like, what is the potential exactly. As long as the potential is regular and finite.
So this RG is defined in the matrix model,
Yeah, this is
and
the,
it's supposed to be equal to the Z
yeah,
of the.
yeah, this is there.
Okay.
And like, whatever is inside the integral is there.
Yeah.
And what's the coupling constant on both? I mean, is it only n that you have the size of the matrices that gives you the only coupling constant, or?
For coupling constants for?
So is there some notion of, so normally in ADS-CFT is a weak, strong, coupling duality, when one
Ah.
side is weakly coupled, the other is strongly coupled.
Yeah.
Is there an analog of that statement here?
I don't know. I don't think so, but I mean, like, I don't know.
But you were using some large n expansion in the matrix model.
Yeah, I mean, you
So-
could say that's.
So N gives you some sort of
Yeah, but,
Something.
I'm not sure.
a one over N or whatever.
Yeah, I mean, so that like, yeah, that's the thing, there is this dictionary between what goes on in matrix model and what it corresponds to when it comes to ADS-AFP, like in JT gravity. So, here, which all of these are, like, there is the corresponding counter term in matrix model. And not counter term, something that represents that. But, like, I don't know the full dictionary, so maybe there is this, like, instead of like these strong coupling here, there's something in matrix model, I don't know.
I mean, what would be a typical, is a typical parameter we can define in the matrix model?
Yeah, and for truth parameter, you need to like have this potential to like, so potential form should be there. We don't care about that. Like, potential is something very, like, it's from what I've read in literature, it's quite monstrous here, but people don't generally calibrate what it exactly is. But as long as it's been behaved within our domain, people just touch it. But maybe, yeah, maybe, like there might be some something going on there, but I don't know.
Let's try to speak once again.